Welcome to Design and Manufacturing Engineering channel. Today, I'm going to share you a new lecture on computational fluid dynamics simulation using SolidWorks Flow Simulation analysis. Specifically, I will be demonstrating how to set up a transient simulation analysis for optimizing the design of blower and ducting. Shown in the video is a result of the analysis which shows the streamlined animation of the fluid flow inside the system. So, let's get started with the simulation setup. Here I already have a CAD model of the system. Let me open the CAD. Here we have the outlet of the hopper where we draw air and impurities through the ducting connected to the blower. The blower sucks the air and impurities and blow it into the cyclone where the air and impurities got separated. Now let me open SolidWorks Flow Simulation software and create a new project. Let me name the project as CFD Transient Simulation. Here we have used a default template. Simply accept it and edit it later. Now let's open the general setting. This is a transient simulation analysis, thus we need to activate the time and also activate the gravity. Initially the default was set up as internal static analysis. So let's change the analysis type from internal to external analysis. Also, we need to activate rotation and select model as local region sliding. Tick the fluid button and change the default water into air. Now let's define the initial boundary condition. Here the unit of temperature is in Kelvin, but I am comfortable in using Celsius. So I go to unit and change it from Kelvin to Celsius. Also, I want to change the unit of angular velocity to RPM. You can also customize your units depending on your preference. Now let me define rotating region. The rotating region contains the blower blade. But before that, we have to select parts that will be considered as solid and select those that will be excluded in the simulations. They're just there to act as sensor plates. All we need to do is to untick those geometry that must not be included in the simulation. Now let's adjust the computational domain. We must bring it closer to the system, but we need to give allowance especially at the inlet. Depending on your simulation objective, you may bring it very close to the system. In this case, we need to determine airflow behaviors at the inlet, so we must put some allowance to make sure we capture more realistic result. Here is the inlet, and I place 0.45 meter allowance from nearest surface of the hopper and 0.557 meter effective offset from edge of the inlet opening. For external analysis, it can automatically generate a fluid region. But I want to make sure that fluid domain is generated as I intended in the system, so I define a fluid domain. Now let me define the rotating region. This is where the blower blade rotates. We need to define the RPM of the blower and direction of the rotation. Here I have set 1200 blower RPM, but you can also set RPM according to requirements. For the direction, we simply add plus or negative sign and see the vector direction indicated if it points the way we want the blower to rotate. Next, we need to set some goals to put what we want the software to predict. Setting the goals also reduces the calculation time and serves as the basis for the solution to converge. Depending on your specific simulation objective, you can also choose applicable parameters as the simulation goal. First, I set a system goal. I am interested in predicting total pressure, static pressure, dynamic pressure, mass flow rate, volume flow rate, and velocity on the entire system. Let me rename it to indicate these are system goals. The next goal is to set some local goals. I am interested in determining the total pressure at the inlet, mass flow rate, volume flow rate, and velocity. After selecting such goals, I rename them to indicate these are my inlet goals. I am also interested in determining the outlet's total pressure, mass flow rate, volume flow rate, and velocity. Now, I rename them to indicate these are my outlet goals. Both my inlet and outlet goals are called surface goals. We have used those sensor plates that we excluded as solid geometry, as I have shown earlier. The last goal I want to know is the total pressure drop from the inlet to the outlet. So, I added equation goals. Let me name it pressure drop, which is simply the difference between the inlet total pressure and outlet total pressure. Now, we move on to the mesh setting. Let me set the mesh size to the finest, size 7. And tick the Auto Resize button to allow the system to generate more mesh in the portion that needs finer meshing to make more accurate solutions or predictions. Now, we are done with the settings. Let me run the simulation analysis. I am multitasking on my computer, so I will select 14 cores to run the calculations. While the solution is running, we can set some monitoring display. I want to display the total pressure at the inlet, the total pressure at the outlet, and the pressure drop so that we can monitor the current predicted values while the simulation is running. Also, I want to monitor the predicted mass and volume flow rate at the inlet and outlet. We can resize the display to get a better view of all parameters we want to monitor. We can also set calculations control parameters even though the simulation is currently running. This setting will set how the solution will converge or stop. Since this is a transient simulation, I will check the physical time of 2 seconds as parameter. It means the calculation will stop after 2 seconds physical time. For the time step, set 0.0012 seconds. Similarly, I will set 0.0012 seconds as periodic for the full results. Just click OK button to apply, and let's wait for the solution to get completed. On the display, you can also see that the blower is rotating the way we want it to, and the magnitude of velocity is indicated by the color. Now that the calculation is done, let's close the display monitor and do some post-processing to see the results. First, we plot a streamline analysis. I will select an inlet as the starting point and create some seeds as the starting point of the streamline. Here's the result of the streamlined analysis. We can rotate and orient to visualize the outcome. Streamlining can give us a quick insight into what parts we need to modify when doing a simulation-driven design. Since we use integrated CD and flow simulation analysis, we can edit the geometry and rerun the simulations to get an updated result. This way, we can do several design iterations until the result satisfies our specific simulation objective. Before I arrived at the final version of my CAD model, I made 3 iterations to adjust the geometry of my design. Let me plot the other display of the different results. Here, I plot the inlet volume flow rate and mass flow rate. So, this is the magnitude of the inlet mass flow rate and volume flow rate. Next, let me do a surface plot to visualize airflow behavior inside the blower. I'm going to use the sensor plate I made located at the center of the blower. So now we can see the pressure distribution inside the blower. And we can change this to see also the velocity. Now let me adjust the chart setting to get a better visualization of the result. We can adjust the number of color divisions and length of the chart. And we can edit maximum value and even the minimum value to be displayed on the chart. Now we can see a better result of the velocity surface plot, which shows the predicted values of velocity and flow direction inside the blower. You can even make this example better to get a better view of the result. Again, let me go back to Streamline. This time, you see the result of velocity streamline. We can animate it to see how fluid flows inside the system. We can also plot a graph of our goals. Let me stop the streamline animation and display some of the result of simulation's goal. Let me plot the result of inlet total pressure, outlet total pressure, and the pressure drops. Now, we can see samples of the goal plot. Since this is a transient simulation, we either change the value of the x-axis as iterations or physical time, as you can see in the example. Thank you for joining me in this presentation, where we've explored transient simulations with rotating mesh using SolidWorks Flow Simulation software. In my next video, we'll explore computational fluid dynamics in more depth as we conduct a comprehensive analysis addressing specific simulation objectives. Again, I am Engineer Jackie John Felix, a science research specialist at the Philippine Center for Post-Harvest Development and Mechanization. See you in my next video.